cloud so I can record.
Oh,
So
okay.
I think
That's
it's
fine.
recording now. Oh, because you made me presenter. Great. Okay.
Okay. Okay.
So I'm Peter Bohacek, and I'm one of the co-founders of Pivot Interactives, along with Matt Vonk. And Matt Vonk has just finished up his class. He's walking across campus, and so he'll be here in a few minutes. So we were just chatting a little bit before, and I was mentioning, and it's relevant now that we've begun to talk a little bit about that. I'm a physics teacher. That's my primary job. And it's only through physics teaching that I became the co-founder of Pivot Interactives. And I think that's true for Matt too. We both are teachers, and we both are constantly looking for ways that we can help our students learn. And we noticed really an opportunity with video as an alternative to word problems and an alternative to hands-on, that there was sort of this middle gap in between there. Word problems are a great way to be able to present any situation to a student. If you can write it down, you can make it into a word problem, but maybe it lacks context and realism and relevance to students in some cases. And then hands-on obviously is super powerful learning, but also has limitations. Has to be something that you can fit in your classroom, that you can afford, that's relatively safe, that can fit in the time constraints of the classroom. And it's a lot of constraints. And then in addition to that, although the students can learn a lot about what happens when things go wrong, they can also spend a lot of time on what happens when things go wrong. And so we tried to figure out, how can we get video to fit this middle ground? And so we began with direct measurement video almost 10 years ago, and has slowly evolved to this current Pivot Interactives. And the big transition for us was when we changed from a service that was freely available to one where we're charging subscriptions. And so that's kind of what we did not intend to do that when we started out. We intended for this to be as broadly available as possible. And we just reached the limit of what we felt like we could do sustainably as the two of us, as a essentially volunteer project. So 2 years ago, we started this Pivot Interactives. And so what I was really hoping, Matt and I were talking about, what we're really hoping to do tonight and in general with Pivot Interactives, is we want to be responsive to what teachers need and students. So yes, this is a for-profit corporation, but the purpose of it for Matt and I is to build tools that help physics teachers and physics students. So the more input we get, what is it about Pivot Interactives that's working? What is it that's not working? What do you wish it could do? The more of those ideas, the more we can build it into Pivot Interactives. And the more, yes, that means the more teachers will use it. That means Matt and I get more money. And what that really does for us is give us resources to expand it even farther. So we have on the one hand the needs of what people are who log on to this, who are interested in learning about Pivot Interactives later, that view this as a recording. And then on the other hand, we have Jeremy right here, and I assume we'll get to a few other people. And I really am interested in having a discussion, an open-ended discussion about what's working, what do we as developers of Pivot Interactives think it could do, and what is Jeremy and other teachers, what would they like it to do? Oh, and here's Matt Vonk. Perfect timing, Matt. I was just wrapping up my long-winded introduction.
I'm Matt Vonk. I'm a physics professor at the University of Wisconsin, River Falls. Peter and I have been collaborating for about 6 years. And then we started Pivot, the company, about 2 years ago. And we've been selling to consumers for the last year. So that's my short-winded introduction.
That's very short, very concise. So Jeremy, who's a participant here, was an enthusiastic user of direct measurement video and now of Pivot Interactives. And so we were having some discussion. And I think maybe because it's possible that someone who views this as a recording will have no idea what Pivot is. So I think I'll share my screen and do a quick overview of what Pivot Interactives is and what it's about. And then I think we should have a discussion about what we would like it to do, what it's working well, and then also what Jeremy and what Matt and I and Wendy are of course welcome. We'd love to have your input as well, to know like What should we do? How can we make this a more effective tool? So let me share my screen. I think I'd like to show the, give me a quick moment here. I just finished up an activity, 2 actually, today, that I think would be cool to share.
So we kind of write the activities that go along with our video resources with different styles in mind. And so some of them are more like a homework problem. Some of them are more like a laboratory experiment. And so I think for our session today, we're going to mostly focus on the ones that are more similar to a apparatus-based lab, where students can kind of investigate, explore on their own, and develop their own models.
Matt, what's my screen look like right now? What can you see?
The pivot library.
Okay, great. With Carl right in the middle?
Yep.
Okay, great. Yeah, that's exactly right, what Matt said. And actually the 2 that I worked on today that we are can be used either way. They can be used either as an opportunity for students to discover a relationship, sort of more in the style of a paradigm lab, or for deployment, for an application where they already have a model and they want to apply the model to a new situation. So that would normally be, I think, something done on paper and pencil, where students are like, okay, here's a scenario, let's take this model, apply it, see how it works. So yeah, let's look at this one with this pendulum here. So I'm going to open this up, testing the effective gravitational field strength on the period of a pendulum. So Matt and I had this discussion, like, wouldn't it be cool if we could vary the period of the gravitational field strength for a pendulum? So I think Matt's idea was to travel to another planet and set up the apparatus there. And we decided not to do that. So then we thought, well, what if we took the whole apparatus and put it on a giant Atwood's machine and then released it so it could like have a vertical acceleration, and that would change G, but that was too impractical. So we decided on this superconducting solution. So this video, oh, I think I can't mute it. I think I'm going to do it like this. We often have videos in the beginning of our activities that just give the students a tour of the apparatus. So in this case, I'm just going to kind of scan through this. But this you'd have your students watch as an introduction. Okay, so that's a superconducting puck. And we put it in liquid nitrogen. And there's just sitting in there. And then we have this magnetic track. And so if you place the puck on the magnetic track, which is in the shape of a circle, and then pull this bracket that holds it in position, now we can swing this thing, and it swings like a simple pendulum. Small arc, simple pendulum. And then we can tilt the angle of this track. Right, so that effectively can change G. Okay, so Jeremy, I got a question. Do you think students will be able to see how that is really the same as effectively changing G?
Assuming that they have already analyzed forces on inclines, then
right.
I would think so, yeah.
Right, and so this is going to be probably for, you know, an AP Physics C. I think this is in the sweet spot, but I think there are students that could be in an honors physics class or an intro college class that could certainly do this. But that's exactly right. They're going to have done forces on an incline before, so they can figure out kind of how an incline dilutes G.
And Peter, exactly apparent as you were moving the scrub bar, just because it was kind of jumpy. But when you actually watch the video, it's pretty clear that as you're tilting the pendulum up, it becomes faster.
Right. You can just see it swing back and forth.
You can actually watch the video.
Right. Okay. Thank you. So we give the students just a brief bit of introduction and say that this next set of videos allows you to explore the motion of the pendulum at different ramp angles. Each trial shows a different ramp angle. You can select side view or view from above the track. And we tell them the goal. The goal is to create a mathematical model that relates the period of the pendulum to the strength of the gravitational field. And so now we get into this is the the soul of Pivot Interactives is a video instance like this where we have 9 different ramp angles that the students can choose from. And in each case, they have 2 camera views. So it started on this trial 4. And so we can go up here and get a protractor tool. Now, Matt has pointed out before that, like, even this process right here, where they click on the pendulum, the students are immediately having to make some really important decisions. Like, where do I measure this ramp angle? Like, do I measure this angle? You know, like go down here and measure or like, what do I do? And so even that is, I casually just put it over here in exactly the right position, but the students aren't going to know that. So these are very interesting skills that are truly lab skills. How would you use a protractor to measure the angle of this? And we like the fact that there are definitely lab skills that the students are learning when they're doing this. So here they measure the angle of the ramp, and they could do it lots of ways. They could put it across the top here, but then it's kind of ambiguous here where that passes through there. So that's probably the most sensible place. And then they change to the above view. And so we recorded these videos in pairs so that the event that you saw in the last video and this video recorded at exactly the same time with 2 different cameras. And so now with this one, the protractor is not doing us any good, so I'll turn that off. We can get the stopwatch. And so now they can decide where they want to start measuring. Maybe I'll measure when the center of the puck passes through the equilibrium point. So I'll start that. Again, this is a really interesting conversation. Should we start when it's released? Should we start when it's at one of its maximum displacement points? Or should we start when it's passing through equilibrium? And so now I can measure a bunch of swings. Sorry, it's probably really jumpy, but so maybe I go through 10 swings and I measure the total cumulative time for 10 swings. So then we have the data table and graph. So now the students could go down here and say, okay, so this is ramp angle, and I'm going to make that in degrees. And then I could do period, but I think I'm going to do total time in seconds. And then I will put here another column for how many periods I timed. So that doesn't have any units. So maybe for this ramp angle of 30, it took 12 seconds to time 5 periods. So now I need a column to find the actual period. And that's going to be in seconds. And so I can make a calculated column here and say that's going to be the time that I measured divided by the number of, I should have probably called that column oscillations, not periods. So I'm going to hit go and then go back and change that. Should still work. If I go back here and look at the column formula, it'll just show me that I've now done time divided by oscillations. Right, so now I can just go rapidly through here. Students can measure the ramp angle, a time, and a number of oscillations and get the period. How are we doing so far, Matt? Have I missed anything?
No, I think that's great.
So, okay, so here's a key thing that I would say, like, we just went through a whole bunch of decisions that students have to make that are lab skills, like this idea of measuring more than one period and when to start the stopwatch and where to put the protractor. So what Matt and I have been doing that I think works really nicely is flipping this compared to how we would have done it in the past. So we would introduce this idea that we want to build this mathematical model. And our first class discussion would be, full discourse, talking to students and saying, what ideas do you have for how we can design this lab? What's our procedure going to be? Students are sharing ideas. They're slowly crafting on their whiteboards. This is what we're going to do first. This is how we're going to measure this. This is what we're going to plot. Sharing those ideas so that the goal of the first class period is simply to design the experiment. So when they go home, this thing down here that says design a procedure, they will have populated this using their ideas, their classmates' ideas, coaching from the teacher. So they leave knowing, okay, I know exactly what my process is going to be. And then when they get home for homework, they can populate this data table, because that they can actually do on their own. They don't need to have a classmate or a partner or the benefits of classroom discourse to simply go through here and change these and make their measurements. So the next
And
day,
I want to point out that it's not trivial, because there's like 20 videos in that single scenario, and they need to make the right measurements on the right videos, and they need to relate corresponding videos. So like they have to measure the angle on the video that corresponds to the thing that they're measuring the period on.
yeah.
And so even though Peter could go through that effortlessly, for the students, that takes a little bit of time to develop. But we, like you said before, we think that is really worthwhile. Those are decisions that we think that it's worthwhile for the students to make.
Yeah, when we looked at for example, the AAPT guidelines for what represent the lab skills that students should learn in their physics courses, so many of them are these kinds of things, like understanding how to minimize error, right? So then this example of timing multiple oscillations is a great example of how to minimize, I guess I said error, I should have said uncertainty. Things like that, those are skills that normally would be learned, that they would learn in lab, but they really can authentically learn in this environment as well. So then the next day they come back, and so one of the things we do in Pivot Interacts is we try to put in most cases, sample data and notes for the teacher and solutions. And so here is so my data just got overwritten. And so now we have, like I was starting to do, angle, time, oscillations, a calculated column for period, and then so let's just plot that. So if we plot period on the vertical axis and the effective strength of the gravitational field, so we get this thing that students will hopefully recognize as, well, first of all, not linear. And then if the students are not new to linearization, they'll recognize that that's probably either an inverse or an inverse squared. But it's really not either of those. It's 1 over square root. So they will have to make a calculated column and mess around with that. Figure out, so here I've made a calculated column with 1 over the square root of g sine theta. And so if we plot that, I think the word for this is unbelievably linear. When we did this video, it was only a few months ago. Like, we just went through and measured the data, didn't take any particular extra care, and look at, it's just amazing. Like these patterns, right? These patterns in nature that are underlying, they just come right out and stare at you in the face. And it's amazing to me to see how good that works out. And I think it's good for people to know that Matt and I, we don't manipulate the data. We took those 9 trials in a row and edited the videos and put them up there, and these are the measurements that came off of them. So it's authentic scenarios and phenomena that the students are measuring.
And we've noticed that even small deviations from the expected value that Peter and I would kind of brush off, often for our students are really, they want to read meaning into them. And so, like, if that's the point of the activity, that's fine. But for many activities, it can be very distracting if you want to show a particular relationship and the students are finding it doesn't really work, or like an example that Peter often points to is with just a standard pendulum. If you change the mass, typically the bigger masses the larger masses are physically larger, so that changes your radius or the length of the pendulum, and so the period does change with mass. And so we try really hard so that our activities come up with data where the students are able to see the relationships without being kind of distracted by these the intrusions of the real world.
Right, right. And sometimes we want them to see that, right? Sometimes we want them to see that this model is oversimplified and that in real life it doesn't work. But we don't always want them to see that. We also
we
want
don't
them.
necessarily want to start with that.
We don't want to start with that, right?
We definitely have some cool examples where the model starts to break down, and we'd like to talk about those as well.
Yeah, and we think, right. So in this case, it doesn't. Like the model is amazingly describes the motion of this thing. And so now from here, it's kind of in the style of an AP Physics C question. So it gives them some prompts about designing the experiment, and then asks them for the relationship they found. So when we do the linear fit, here's the relationship. And then asks them to, so we're viewing it with the teacher notes showing. So it asks them to use the slope to determine the length of the pendulum from the slope. Looks like I better take that last 3 words off of there. And so when they go through and use the slope and compare that to the model for the period of a pendulum and predict the length, they get 1.99 meters as what ought to be the length of the pendulum. And I just finished this a few minutes ago, and I haven't gone back and checked. So I'm really curious to see what is the length of this pendulum. So if we put that back to here, bring up the interactive ruler. Well, that's interesting. Do I have that right? Okay, well, that's why I shouldn't do that right now. So it actually looks like it's not, because there's the center of the pendulum. It's more like 16. So I have to go back. We're not, is that right? No, 15, 16, 17, 17 and a half. So I am going to have to go back and see why that data is not quite right, because it isn't. Or, so this is a perfect example. It's a little bit embarrassing to have it right in the middle of a live recording, but I don't know why that is. So is there something about the way I did the calculations that's wrong? Or is the effective length of this pendulum really that close to the bottom of it as opposed to at the center of mass, which is what I would have thought. So we will have to look into that, and then we'll put some teacher notes on there when we figure that out. But this is probably a good time to open it up. What do you guys think? What do you think of that overall? And then do you have any suggestions why we are seeing that deviation?
My first guess for the deviation is that it also is rotating. So not only is it not a point source, but it has that rotational energy. So I wonder if that changes either the period or something related to the energy, how high it goes.
So it's really not a simple pendulum. It's more like a physical pendulum. Is that what you're thinking, Matt?
Yeah, that'd be my first guess.
Yeah, interesting. So so that's. I think the other thing that I'm going to have to check is go back and check the calibration of this ruler. Although I'm pretty sure that's right, I can see that I'm almost positive that the diameter of this disc is 40 centimeters edge to edge. Okay. Anyway, moving right along.
Did you get the center right?
I think so.
Okay.
Here's another one that Matt, you're familiar with this one. So if you'd like, we just redid this one and made a new version of it. So some of the data is maybe a little bit different from what you have experienced before, but the video is the same. So do you want to talk about this one?
Sure. Yeah. So let's just, can you play the video?
Yep.
So if you noticed on the upper right, the ribbon was cut and then the whole thing accelerates. So even that detail took us a while to develop, because it turns out that in these kinematic problems, it's really important to know exactly when the object is released. And in the past, we would rely, we'd have someone hold it and then let go, and it was just hard to get a clean release. So we found that cutting the ribbon allows you to determine within one frame exactly when it was released. So yeah, go ahead and play it. Each video has different tools that go along with it. This has a stopwatch and a ruler. So you can reset the stopwatch at that time. you can see a weighted Einstein is pulling on the cart.
Right, so there's Einstein.
And then in addition to this scenario, if you can select different videos. So Peter, can you go ahead and change that?
Yep, and this instance has just the two options, Matt. So can you see the text there?
Okay, yep. And so now Einstein has moved, and so now he's riding the cart. And so students can again measure the acceleration. And from both videos, they can separately determine Einstein's mass. And what I love about this one, talking about looking at ways the simple model fails, is that friction in this one makes Einstein appear more massive than he actually is, right? Because friction makes it accelerate more slowly, and so it would give you a mass for Einstein that's a little too high. Whereas when Einstein is hanging, friction slows everything down and makes it seem as if Einstein was a little too light, a little lighter than he is. So if you do these with your students, they're going to get two values. They can independently get values for Einstein, and they're going to be off a little bit. And it's interesting that they're off in particular ways, because friction acts on one to make Einstein seem heavy, and on the other one to make Einstein seem light. So from that, I just love it, because I feel like students so often will say friction. They'll like, why didn't you get the right answer? Oh, friction. And they don't really think about how it acts, or that it could act in two totally opposite directions in a very similar scenario. So I think it's a really interesting problem. Probably not to develop a model, but once it's developed, to apply it to a real world situation.
Right, and so Matt, we did the data. So we had several trials of this, and we had put them previously up on the Direct Measure video site. But I just never had time to go back and really go through and analyze them. And so over the last couple of days, one of our student workers kind of combed through them. We found a bunch of mistakes, called them out, and found these two examples. And so if you go through and measure the acceleration, so I have to scroll back up to the top and show the answers. So, so we give a full solution so that people really can see. And so when Einstein is hanging from the string, he comes up, we get an experimental mass of just about 100 grams. And then when Einstein is riding the cart, we get an experimental mass of about 108. So just like Matt said. And so then we also included in this a picture of the Einstein sitting on a scale, so that we see if you measure him not on the system, is a mass of 105 grams. So it's just kind of perfect, right? That they're close enough, 100, 108, right? It's less than 10% difference. And that either one of them is just a handful of a percent difference from what the mass of Einstein is sitting alone. And so it's this balance, like Matt was talking about before, like, yeah, we want them to see deviations from ideal models, but in such a way that it reinforces the ideal model rather than causing them to be skeptical of it.
And so what I did with my class is have them estimate the uncertainty. So then the first question is, when they get these two disparate values, is that significant? Or is it just lost in the uncertainty? And in this case, it turns out that they are significant. The differences are significant. But it allows them to kind of put in practice the propagation of errors and understanding experimental uncertainty.
Right. Yeah, so that's for a high school student, it's probably a challenging example of applying a model to a new situation, but it's a really interesting one, and it has lots of the ingredients that we like, that you can really get accurate data, that the students can see the scenario really clearly, and that the types of error that they're going to run into are interesting. and contribute to their knowledge. You have another favorite one? Since I've been working on these for the past few days, those are my two current favorites.
I love the wave properties.
Oh yeah. Oh, but when you get a chance, Matt, you should. Oh, I haven't published this yet. I'm going to publish this one tomorrow. The 2D relative motion with drone. Man, is it coming out! It is really, really cool. But wave properties, sure, we can show that one.
I love the drone flying back and forth too.
Yeah, we published the 1D relative motion, but AP Physics C teachers are going to really, I think, be happy to have a real version of, where you can quantitatively measure motion from 2 frames of reference. Should we quickly show it? Jeremy, you teach AP Physics C, right?
Yes, I do.
Yeah, so we got
hit preview, right click on preview and open it in a tab, and then we can go back to it.
Fair enough. So here, I'm going to jump right down to this one. So we'll start off with a video. So this is a drone hovering over one of our practice fields. We took this towards the end of the summer. And so the video there, can you see it? Can you tell what that is from the video? That there's a dog running across this grid. And so, so Jeremy, you said your students were doing the Jesse Diggins video, right? And did they find the dog in that video?
They're doing it tomorrow. I found the dog today.
This is the same dog. So it turns out every single time we've gone out onto this practice field, the people who live a few houses away from our school are walking their dog. And so we're like, okay, what are we going to get the dog to do? So the students who were working on this summer, they're like, hey, there's that dog. And they went and so I don't know if you can see, it's probably pretty hard, but right from outside of the view, one of the students who made this video threw a tennis ball. And so the dog is just following the tennis ball. And so that's how they got the dog. That's how they controlled the direction of the dog.
And then what about the grid? What's the grid?
Yeah, so the grid, they made that. They laid that down with pieces of the weed suppression fabric that we got at a garden center, and then they cut the long roll of fabric into narrow rolls, like basically strips. And then they stapled it down to the ground using these wire staples. And then it actually took them 2 days to get that grid as perfect as that. So it's 5 meters. All the distances are 5 meters, and it's really totally uniform. That was
beautiful.
Quite a project. Right? So here the students can just measure, okay, so now we can measure the velocity of the dog in 2 dimensions from the frame of reference of the ground. We're watching using this grid here. And we have, let's see, what is this one? Oh, this is the same idea, but it's students walking, and there are a bunch of different trials. So you can just see a student starting from a different location and going in a different direction. And so same idea, they're still just working on how do you measure the velocity in 2 dimensions of a person from the...
Oh, you can see their footprints.
Oh, really?
Yeah.
I didn't notice that. Okay, so then we just do the drone. We have the drone moving. And so in this case, it's just moving east. And so, the students are still there, making sure that people know that this is real, not animated. So they're on the ground. Can you see what they're doing? They're doing like calisthenics. He's doing his sit-ups, and she's doing and then my son is lying there doing nothing. Right? So now so with this one, there's this measurement tool where now they can put a dot on the ground. So right here is a dot that's just stationary. And so now they can use that dot as it moves across the grid to measure the drone's velocity in the frame of reference of the ground. So then comes an interesting scenario. So here we watch the student from the frame of reference of the ground just walking directly north, and the drone moving directly west. And so now students can use those 2 motions and see that the motion of the student with respect to the drone. So now you can see that the student starts in the far lower left, but as they're walking north from the perspective of the drone, they're moving to my right across the field, right? So now they're like midway across the video. So their motion has been in this direction. So can the students use the vector addition to predict that angle?
And what are the tools available?
So for this one, they have the dot that they can use to measure the drone's velocity. And they have a grid as well. And this grid is also, it's fixed. So, right, so it is, so they can go like this. So that grid is measuring velocities from the drone frame of reference. So what we might do is withhold this tool while they're doing this. Because if they have this tool, they can directly measure the velocity of the student walking from the drone frame of reference. Whereas if we don't do that and they can just use the dot to measure the drone's velocity and the grid on the ground to measure the student's velocity, so they can make a prediction of if I did measure it with the grid from the drone's perspective, what would I get? But then we thought also what would be cool is to ask them, if the student walked at that velocity, then at what angle would they have to walk in order to make it so that they appear from the drone's perspective to not go diagonally across the screen, but instead to go straight up? And so we give them a bunch of different angles. So I'll just grab one. So we can see the student standing right here, and presumably she's going to start walking. So I happen to choose the angle where she's not going up the screen at all. She's moving ever so slightly faster than the drone. So that was a poor choice on my part. Let me just choose a different one. And they can also select the angle. Select the direction of her angle. Is it to the right or to the left? I think that would be fun because I think in most cases students have a hard time, again, visualizing those three vectors and the direction of those three vectors. So here we have her angle to the right. That makes it worse. Now she's walking much more rapidly to the right across the screen. So it must be one of the left choices. Okay, so that's a prototype, and we have more examples with both objects moving. Drone diagonal, person lined up with the grid, and then what if they're both moving diagonally? So those are even more advanced than what you'd see, I think, on the AP Physics exam. Suggestions about that one? Matt, you haven't seen that before, right?
What is that, a puddle on the left? What's the big beige thing on the left?
That is the it's the baseball practice field. This thing?
Yeah.
Yeah, that's third base, I think, right there. I think that's the pitcher's mound.
Interesting.
Yeah, drone perspective is really cool. So that'll be published soon, and I think again, so this is more in the lines. It's not a lab, right? In no way is this a lab, but it's I think a lot more interactive and interesting, and hopefully more helpful when students are tackling that abstract difficulty of using vectors to figure out 2D relative motion. All right, what did you want to show, Matt?
Before we go to waves, can you do the drone one that goes like this?
I can't see your gesticulations.
Oh.
All I can see is my screen.
Einstein riding a drone.
Oh, Einstein riding a drone. Yeah. Who knew that the drone was going to be so useful?
So what I like about this activity is that it's so, like, my students struggle to differentiate position, velocity, and acceleration, and especially like positive and negative values. They tend to think that if the velocity is positive, the acceleration has to be positive. Like they feel like they have to go hand in hand. And what I like about this activity is that it's really easy to see that they're all very distinct, and that their signs don't have to necessarily correspond. So one can be positive, the other one can be negative.
Aren't our search tools great? I can't find an activity so I must have tagged it using this tool. So sorry.
Yeah. So what it shows is Einstein on a drone, and it flies back and forth between the left and right side of the field of view.
Here it is.
Yeah.
Yeah, so this is a video of the drone rather than taken by the drone.
Yeah, so I always encourage my students just to watch it first.
That sound you hear is the sound of the drone in slow motion.
So the way that I would use this is talking about, like, if we call the right direction positive and the left direction negative, and we put the 0 right in the center, then anytime the drone is on the right side of the screen, it has a positive position. And if it's on the left side of the screen, a negative position. So that's pretty clear. Also pretty clear for my students is its velocity. If it's moving to the right, that's positive. If it's moving to the left, it's negative. But then the fact that they can actually see the tilt of the drone clues them in as to the acceleration. So if it's tilted left, it's going to have a negative acceleration. It's going to be accelerating toward the left. And if it's tilted to the right, it's going to be accelerating to the right. So in that way, they can see kind of that phase shift that happens between when the acceleration changes right there, as it's tipping now to the right, but that it still is moving to the left for a while after that. Or, yeah, okay. Tip to the left, it still moved to the right for a while before it finally came back. So I just think it makes it really clear to the students the difference between the acceleration and the velocity.
Yeah, so you can see here that the fan motors are pushing it to the right while it's moving left, which is why it slows down. And then it changes direction and it's still pushing to the right, which is why it speeds up to the right. So we thought that was a nice visual example that let them hopefully make a connection between the direction of force and the direction of acceleration. And can you guys see that Einstein is on the drone right there? Is that obvious?
Yeah.
Ride 'em, cowboy. Any questions so far?
I think not yet.
Okay. All right, Matt, you love this one. You keep going. You're doing great.
Yeah, so can you just run the video and we'll watch it? So what this video shows is a large spring, and it's horizontal. And we built what we called the wave wiggler. It's a modified stereo speaker that's connected to a lever just to amplify the motion that oscillates the wave 5 times. And then Anna, she was a grad student who was working for us for a summer, sent the signal that moved the stereo speaker. Students can click on the tools and open up a stopwatch and a ruler. And with those tools, determine the period, the frequency, the wavelength, the wave speed, and the amplitude. So 5 things. And those are 5 pretty abstract things. But we've found that when students are interacting with a video, even abstract things tend to be much more concrete for them. So we could write relationships between the wavelength and the period on the board, like as we're introducing a topic. But if they can just interact with them a little bit, we find that they're less confused by them, and the concepts become more concrete in their minds. So that's pretty cool. Like from one video, they can do all that. I'll just point out that we made a decision to make the horizontal ruler, the vertical ruler fixed, and the horizontal ruler not fixed, because we found that it's kind of difficult to measure the amplitude correctly. And it's really sensitive to getting that centered on the zero. And that's hard to do when the wave is oscillating around. So for the most part, we want students to be making those decisions. But in this particular case, we made the decision to keep the vertical ruler fixed so they can get a good measurement of the amplitude. Okay, so after interacting with one video for a while, they can measure a bunch of things. In this particular activity, students can choose between 3 different tensions, 5 different amplitudes, and 5 different frequencies. So what appears to be like one video is actually 75 videos.
Right, because they can do each of these independently of the others, right? So for every combination of amplitude and frequency, they can choose 3 tensions.
Yeah, so this was a hard video set to get, for one, because we didn't have a great way of controlling amplitude. When we would change the frequency, like the amplitude would sort of change. So we ended up taking hundreds of videos, and then we selected the ones that had constant amplitudes. And we made this 3-dimensional matrix of videos that students could then explore. And so this gives students a ton of freedom. Like one set of students could say, oh, I wonder if we increase the frequency, like if we shake it faster, is the wave going to move down the spring faster? Like that would be a reasonable hypothesis. And the students can design an experiment and test it out. So it looks like Peter is increasing the frequency and hitting go. And so we'll watch if that looks any different. And in this case, oh, there it goes. It's pretty obvious that the wavelength decreased, but it turns out that the speed didn't increase. It was the same speed. And so other students in that same class could say, I don't really care about frequency, but I wonder if we decrease the amplitude, like if we barely move it back and forth, I wonder if that will slow the wave down. So then they can design an experiment to do that. Peter just showed you a wave with a very small amplitude, and it turns out that even that doesn't change the speed of the wave.
I need to point out that Matt said we selected for ones that had the correct amplitude, but right, because the amplitude turned out to vary with frequency. But that's all we selected for. There was no other, like all of the other parameters came out the way they were supposed to. It was just that interdependence between frequency and amplitude we had to select out for.
And then other students in the same class could say, let's see what happens when we change the tension. Students could use this to develop a model for the relationship between wavelength and frequency. And so for each of our activities, we have a set of instructions that we think are good, but we are really looking also for the community to see how they would best take advantage of these resources. Because obviously there are other people that are much better at doing that for their particular students. They know the approach they like. And so one of the features that we've currently added to our platform is the ability for instructors to modify our instructions. So they can make it much more modeling friendly. They can put it in the language of the modeling community, and then they can publish it so that their peers can use it. And we're really excited about that because we think that, well, frankly, that other people could do a better job than we can.
Thanks. That's exactly what I was going to say. It's like I think when we come up with these videos,
I was trying to find a diplomatic way to say it, but I couldn't.
No, we really recognize that the teaching community has way more cumulative creativity than Matt and I do. And so that was actually an intention from the very beginning was to make sure that people recognize that we don't think this is the only way and probably not the best way to use this particular set of videos. And so we want teachers to feel creative. And now this new feature, it looks a little bit different because I'm a content editor for Pivot Interactives, but any teacher that opens this activity up can click this share to community, so they can say, no, you guys got it all wrong. Let me rewrite it. And now I will share to community. And so now that's right. This is brand new, that now you can look on here and see, here are users who have taken our activities and fixed them and then re-shared them with the community of teacher users on Pivot Interactives, right? So this one, I looked at this one that James did. It's quite different than ours. It's great. It's really a great activity. And so I hope that people will go look at that and say, well, maybe James's is better than what the people at Pivot Interactives did. And it is a great activity.
Yeah, sometimes I think if we're writing, we want it to be easy for any instructor to use. So I think sometimes we err on making it overly scaffolded.
Yeah, absolutely, Matt.
And so we really want to empower instructors to say, no, I'm going to be in the classroom with my students. If they get stuck, I can help them. I'd like to give them a little less direction and give them a little more freedom.
Exactly. Well, since we were going to have an interactive session, we instead talked nonstop for 50 minutes. So I'm going to stop sharing my screen, and let's take a few minutes and talk about some other things. Wendy, I'm curious, had you had much experience with Pivot Interactives before?
I had never seen this, and we are now working with distance learning workshops, and I think that would be a nice way to get some labs in, because that's the difficult part. Modeling workshop, we think they are best if you do them, if you have a real face-to-face workshop, but that doesn't always work. Teachers may not be able to spend 3 weeks of their summer, to go somewhere. And then, but the lab part, that's the hardest part. So this is great. And then I don't know that much about physics. I never went much further than the buggy lab, and we had an actual pendulum, but yeah, I can see this work so nicely with the physics workshops, the distance learning workshops. Yeah, I love it. And the fact that it is interactive. And I also, so I don't know what kind of platform that you're using, but so for AMTA, we have the curriculum that is, I don't know, curated, I don't know, something by AMTA.
Yeah.
And the fact that now you have, there were 3 or 4 people's names that I recognized, that they are able to make changes and have their name there. I think that's something that for AMTA that would be great as well. But we're not there yet.
Yeah. One of the things I'm hoping they'll do is they also can add tags. So if you're an author, a user author like Jeremy, he can go on there and say, like, okay, I'm a modeler and I've made this. So we're going to use, language that's familiar to modelers. Then he can add a tag to it that says this is a modeling activity. And then in that community library, you can specifically search and say, I want to filter on activities that are written by modelers.
He could say it's a paradigm activity. He could say it's.
Exactly. Deployment. Yeah, exactly. That's we try to build that flexibility in because, right, we know we have such a tiny fraction of the total amount of the community is going to be vastly more creative than we can be.
Yeah.
Well, I appreciate that you added that community feature so that we can all build things that work for the way that we teach. Like this is an AMTA webinar, of course. So like there's a specific way that I'm going to want to do my paradigm labs or deployment activities, and so being able to take those videos and just change the format of it to fit my approach is a really powerful tool and really helpful. So thanks for that.
Cool. That's great. Yeah. Well, we're really glad to hear it because that all of the new features that we've done since we launched, okay, there were things that we knew just needed to be fixed, but mostly the big ones, the cool features that we've added in the past 12 months were teacher recommended. They were like teachers who said, we're using this, and this is an area where I think you can improve it. And then we get with them and say, well, what do you mean? How would we improve it? And then we say, well, if we fix it like this, would that do it? And we build these ideas. And then we're like, when we settle on something like this is going to solve this teacher's problem, then we build it. And, you know, we want to do that more. We just, the more input we can get, the better we can make the platform.
Mm-hmm.
Yeah.
And I've noticed that there's been a lot of growth in the chemistry content you have.
Yeah. Yeah, we are excited about that. We initially thought that Pivot Interactives would be great for, or video, interactive video in general would be best for physics. But we've been amazed how the chemistry thing. So because, boy, we should have done this. That's a great suggestion, Jerry, but we should have done it much sooner. The chemistry ones, I think in some cases, well, I don't know how I would do a comparison, but I'm going to quickly do a share screen again and look at one if we have a moment.
Yeah, so that was our big push this summer, was to come up with a curriculum that would be sufficient for a year of introductory chemistry. And so we kind of looked at typical topics that instructors cover during that time and thought about ways that we could do it. And I have to say, I was probably the biggest skeptic about how chemistry would work in a video format. I thought the videos would just be, you know, people putting stuff into beakers, and they wouldn't be that interesting. They wouldn't be that visual. And I have to say that with the input of especially Peter and our student workers this summer, they had some great ideas, and they've really created not only good videos, but like visually compelling, interesting videos to watch. And they've pulled out some important chemistry concepts in kind of interesting ways.
So when I flipped screens, the Zoom application crashed, and
Yeah.
so I came back, and so now the recording is not. So hopefully it did record. Hopefully the fact that I stopped recording abruptly. Otherwise, we have to do this again. Let's start again. Ready?
Hi, I'm Matt. Sorry, I'm late. It says it's recording again, Peter.
Oh, it does?
Peter wasn't the host anymore, so now you're the host, and now you should be able to share the screen again.